Good afternoon, everyone. Welcome to today's presentation, and I thank you all for attending today. Our presentation today is Human Factors Engineering and Design. However, before we begin our presentation today, I would like to take a few moments to review and highlight some of the necessary CLE tracking requirements, as well as other general information that we would need to cover. Today's webinar will cover a brief background of human factors as well as the definition of ergonomics and how occupational ergonomics and biomechanics can lead to improved performance and reduced risk of injury and its importance to the legal community. CLE requirements for those attendees who would require a code word for tracking purposes. The code word for today is human factors. During the presentation, we will take short breaks, and during that time, we will ask you to enter this code into the chat feature for CLE reporting purposes. The chat feature, again, is located to the right of your screen, so you would just simply enter the code word when I ask you to submit that. Dr. Rosenberg also welcomes your questions today, so again, please use that chat feature to submit your questions throughout the presentation. We will hold them in the queue, and then during intermittent breaks, we will submit the questions to Dr. Rosenberg, and he's very excited to answer any questions that you may have today. Tomorrow morning, we will send out an email with a link to an archived recording of the webinar, so all of our attendees will receive that link. And if you have any questions, you can certainly contact us here at TASA. Also, before leaving the presentation today, we ask that you take the time to complete the survey that will appear on your screen after today's program. The survey is also a CLE requirement in some states, so we do urge you to just answer this brief survey, which again is at the end of following the presentation. Our presenter today is Dr. Craig Rosenberg. Dr. Rosenberg is an accomplished human factors engineer, user interface designer, software engineer, and systems engineer. He has extensive expert witness experience specializing in user interface design and human factors issues. Dr. Rosenberg has worked on a large number of user interface projects for a wide variety of high-profile clients, such as Boeing, Samsung, Google, Disney, the United States Army and Air Force, the Federal Aviation Administration, and others. He developed the first two-way pager for AT&T Wireless in 1995 and 96. Dr. Rosenberg is the founder and CEO of a Seattle engineering consulting company focusing on location tracking applications for GPS-enabled smartphones, as well as a co-founder for two medical device technology startups. Again, I want to thank you all for participating in our webinar program today, and I'm going to turn the presentation over now to Dr. Rosenberg. So we will turn the presentation over to Craig. So Craig, the presentation will be in your hands.
Excellent. Thank you very much. Appreciate that, Carol. Good afternoon to everybody. I guess good morning to those that are on the West Coast. I'm presenting here from Seattle, Washington, where I live. My name is Craig Rosenberg, and my contact information is there on the front page if you wanted to contact me afterwards regarding questions you might have. I'm excited to present to you today about the field of human factors, which is a field that I'm very interested in personally and professionally. And I have an overview presentation for you on this field. So, first chart. What is human factors? Human factors is a very multidisciplinary field, and it incorporates a lot of different things. I present here a couple different quotes and descriptions of what the field of human factors is. I like to say it's taking into account the capabilities and limitations of human beings during the design, manufacture, and operation in order to optimize safety, efficiency, and reliability. I believe that captures the essence of human factors, but there are different ways to describe it. The study of how humans accomplish work-related tasks in the context of human-machine system operation, that perhaps is another more modern interpretation of what human factors is. Right below it, it said an interdisciplinary science concerning influencing the design of manned systems, equipment, operational environments to promote safe, efficient, and reliable total system performance. I won't read through all of these, but I think those three give you a good flavor of where human factors lies, and certainly there'll be a lot more charts that will explain it. What are the benefits of doing human factors analysis, of incorporating human factors into engineering? Well, for one, there's enhanced safety, there's reduced error rates, improved performance and efficiency, and overall reduced life cycle costs. So it'll cost a little bit in terms of time and effort up front to incorporate human factors, but the benefits will pay back in these areas. And what are those areas? That the different interdisciplinary fields, if you will, that feed into human factors. Well, psychology is a big one. There's clinical psychology, experimental psychology, organizational psychology, educational psychology, different branches of psychology, because human factors really lies at the intersection between the human being and understanding the capabilities and limitations of the human being, which is psychology, to engineering and equipment, design of interfaces, design of workstations or environments in which people are interacting with. That's the engineering realm. In half of the universities in the United States, human factors is taught in psychology departments, and then about half of them they're taught in engineering departments. It is the intersection between people, procedures, and equipment. That graphic in the lower left there, that definitely is really where human factors lies, because you need to take into account all of these things to understand how humans are interfacing with their world. We want to take into account the technical, the individual, the organizational context, and the operational context. All of these need to be taken into account. So a couple charts on the history of the field. Started in the late 1800s through the early 1900s. Frank and Lillian Gilbreth were doing time and motion studies in the workplace, looking at performance of skilled operators, fatigue, equipment. This was driven by the Industrial Revolution, and it really represented the forerunner, if you will, or the foundation of human factor research. But the workplace at that time was very task-oriented, and it was associated with fitting the right people to the job. So there was a certain job that it was designed in a certain way, and you need to find the right person to do that job. It wasn't the other way around, which it is fortunately now, which is, well, design the job, design the equipment, the procedure to match the capabilities and limitations of the human being, which is how it is now. So moving forward in the 1945 through 60s, human factors was born in labs in the United States and Britain. There was a Ergonomics Research Society. I'll talk about ergonomics in a moment. There was first look in human factors. There was continued growth through 1960s through 1980s, mostly in military research and research related to the space race. But it branched out beyond that into automobiles, computers, other consumer products that were being developed starting after the 60s that involved much more of a cognitive component. Because human factors really comes into its own, if you will, in that when you incorporate the cognitive elements and how users use devices that are more complex than something that is just physical. Here's three things really drove interest in human factors and understanding of the importance and need, and that is the development of computer systems and designing computer systems that were more user-friendly or people-oriented, as I say there, and the presence of various very high-profile disasters such as 3 Mile Island, Chernobyl, Bhopal, were all brought a lot of attention to human factors and the human element in these disasters and how could they be averted and avoided through better design. Various lawsuits came to recognize the need for experts in explaining human behavior, explaining the design of products and systems. So the need for human factors professionals was also driven by the courts and attorneys. So there's a link between human factors and experimental psychology, which is the study of the mind, cognition, the brain, behavior, why humans think and behave the way they do. And we want to be able to study human behavior in the context of technological systems. This is an image of the flight deck of the space shuttle. And being able to operate a complex system such as this, and there's many examples of complex systems, takes a lot of understanding about how humans process information and therefore how to design. We're not going to change how humans process information. That's something that has evolved over extremely long periods of time as humans have evolved. But what we can change is how we design equipment, procedures, environments to best take into account how we process information, and our sensory capabilities, our cognitive capabilities, and our motor capabilities are fairly constant. They're not going to change much over a few generations, or perhaps not at all, but our technology we can change to suit the human population that will be using that technology. One more slide on cognitive psychology and human factors. Here's some cognitive issues that should be considered when designing equipment. This is a picture of an FAA en route air traffic control center for high-altitude aircraft separation. We need to take into account memory, attention, response to stimuli, how information is coded, decision-making, potentially even disabilities and abilities of the human operators. How much cognitive load, I'll talk about that in a subsequent slide. Various degrees of level of automation, that's a very important topic in terms of what is the right level of automation for systems, and when automation fails, how quickly can the human beings pick up and recover from a failing, if you will, of an automatic system. So one of the most important areas where human factors research can be applied is in the design phase. How should we design the equipment or the process, whatever the task at hand is, to take into account the capabilities and limitations of the human population that will be using it. It's usually driven by needs or requirements, sometimes by regulation. The drivers can often be safety, reliability. It can cost more initially, as I mentioned, but this effort will return multiple times, will yield multiple dividends, if you will, in improved safety, performance, reliability, and efficiency. So four, I should say, of the overriding design principles has to do with making your product, your system, as bomb-proof as possible. expression I've heard used in the field. So you want to make the right way to do something the easiest way. You want to make, ideally, and very safety-critical applications, make the right way to do something the only way to do it. You provide safeguards to prevent it from being done the wrong way, and you give operator feedback if it was done the wrong way. In the case of a more complex system that has many different modes and operational features that the system can perform, it can be difficult to make the right way the only way to do it. Some various design considerations, it has to, are these elements here: safety, performance, reliability. What is the task that you're trying to accomplish? Usually design is done in a task context. So a task will be identified, and then the system, the equipment, the procedures will all be designed in order to optimally accomplish that task. And in a case like an aircraft, there may be hundreds of tasks that aircraft does. I mean, at a high level, it's transporting the occupants from point A to point B, but when you break that down, that will break down into hundreds of different tasks that the pilots need to do to safely accomplish their higher level goal. Looks like I'm at a question section.
It does. We're at the first question section. So at this time, I will ask the attendees, actually first to enter in the code word or the password for today that was announced at the beginning of the presentation. And again, we do this for CLE tracking. As many of you know, some states do require us to track for the CLE credit. So, and many of you were here and are now entering in that password. But while they're entering those, I do have a question for you, Craig. And here's a question. How does human factors enter into multitasking, specifically driver distraction like texting? What is it about we humans that think that we can do, more tasks or more than one task at a time, especially when we're in a situation like driving?
Yes, that's a great question. Multitasking it's an active research area in human factors. People like to multitask. People are easily distracted and can receive sensory information, if you will, and be distracted from a primary task. Dr. Clifford Nass, actually, from Stanford, unfortunately he recently passed away, but he did a tremendous amount of research in multitasking along with others, and discovered, it actually hit the mainstream news a couple of years ago about how the inefficiencies associated with multitasking and how essentially it makes one less efficient to quickly bounce around between multiple various tasks, and it's much more efficient to do one task for a good length of time and then switch to and do the next task for a good length of time. At the end of the day, if you will have been much more productive in accomplishing all your various tasks. And this is because of something called context switching cost. So as you switch from one task to another, you need to reorient yourself in terms of what your goals are, your working memory, what the rules and processes you're using to do the second task, which may be very different from the first. Now, to finish up the answer, I think what you were asking, Carol, it definitely had a safety context, too. Texting while driving. Driving is a task that has a large safety component. It's very easy to injure or kill oneself or others, and you need a high degree of attention on the primary task, which is safely navigating a around the road. Now, if you do texting, I mean, I think it's obvious to all. For one, it will take your eyes off of the road and onto the display that you're texting on. But what's very interesting is there's been studies that show that even if your eyes don't leave the road, if you have a heads-up display and you're seeing your texting, there's different technologies to present symbology and words and graphics in the line of sight in an augmented reality kind of fashion. Think Google Glass. So you could still be ostensibly looking at the road, but if you're focusing on texting and the graphics, or even going further with this question, if you're hands-free and you're in a phone call, you're still looking forward, you're not even using the visual information, but you're focused on that phone call, your chances of being in an accident are greater because your reaction time, it will be poorer while in a conversation on the phone. If you have a person next to you and you're talking, it's very interesting in that person next to you will realize the environment that you're in, and if something inherently potentially dangerous is starting to occur, they will adjust their conversation to allow you to focus more of your attention on the road. So there's a lot of different elements to that question. Hopefully I touched on a few of them.
You did. Thank you. That's actually quite interesting that a passenger in the car would be that attuned to the environment. But
yeah, they may not even be aware that they are doing that, but it definitely happens. If you can notice that just by paying attention to it. It's been documented in research. If somebody's changing lanes and the passenger can tell the degree of engagement with the driving task, and when it becomes more critical and that engagement needs to be higher, the passenger will essentially lower their degree of engagement with the driver to allow those attentional resources to be utilized for the driving task. Some of my upcoming slides will talk about attentional resources and probably will be more clear.
Okay. We have a question from Michael, and he asks, how can a human factors expert help in a trip and fall case?
Well, I do have a couple of slides about that speak around that in the future. That's probably one of the more common areas in which human factors experts get involved with cases. It doesn't involve the cognitive aspect of or human factors as much as it does some of the physical aspects, but understanding the environment in which that trip and fall happened, understanding, was it a work context? Was the person always working there? Was the environment that was provided inherently unsafe? Was there any signs or notifications? Did the owner of the property, if you will, had they been alerted to the presence of that hazard prior to the accident happening? The human factors experts are involved with consultation, training, creating expert reports, declarations, affidavits, deposition, and court testimony. So it's really an analysis of the accident. I do have an upcoming slide about accident investigation, and I think that probably will speak to the question because it's just, in general, that is an accident, but there's all kinds of accidents, and doing accident investigation and analysis of why that accident took place, and then potentially opinions as of where the fault of that accident may lie are all areas in which human factors engineers get involved with.
Mm-hmm. And I have one other question. When we just talk about human factors in general, and then we talk about specific accidents, Are there studies between just adults and children? Have there been any, does it show any difference in how accidents can occur in relationship to different age groups?
I would imagine yes. I haven't researched specific studies that show that speak about differences between adults and children related to accidents per se, but there's tremendous number of differences cognitively as well as physically, as we all know, between children and adults, and how children process information and understand their environments, and as well as just the biomechanics of how the muscles and sensory apparati of children work compared to that of a fully grown adult. I would need to look into further to find out who is doing the best work on the field in terms of differences between children and adults as related to accidents.
Okay. Well, thank you very much, Craig. I think that seems to be all of our questions for now, and we will return to the presentation, and we do, I think we have at least another half hour to go so that we can make sure that we meet all of the CLE requirements. So, Craig, the presentation is yours again.
Okay. Thank you very much, Carol. So, related to human factors is ergonomics. And ergonomics is the study and optimization of the interaction between people and their physical environment. Ergonomics concerns itself with the physical, psychological, and physiological characteristics of work. It actually was born, if you will, before human factors, which takes a more cognitive slant at people and their environments. Ergonomics takes a more physiological stance or physical stance of people in their environment. Here are some of the factors that ergonomicists look at: user orientation, the diversity of the subject population, how tools, procedures, and systems, what effect they have on people, various objective data. They use empirical information like most scientists do, including human factors, rather than, common sense, of course, utilizing the scientific method to test hypothesis with various experimental conditions, and taking an overall systems approach that the people, the procedures they use, their environments, any equipment, it's all interconnected, and they all have an effect on one another. None of these exist individually. Related to ergonomics is occupational biomechanics. So here, this is perhaps diving down a little bit further, but definitely in the area of physiology and the physical aspects of work and workstations, looking at how people, the sizes of people, the range of sizes that we all come in, the ranges of heights, weights, forces, reaches. Can this engineer who is a 5th percentile Asian female, so you're looking at a specific subset of your user population, who, let's say she's an airplane mechanic, she's Asian, and she's 5th percentile in terms of height, so height and weight, let's say, so much smaller than the average. Would she be able to accomplish this specific task that's in her job description? Or alternatively, would this 95th percentile Caucasian male of this size and strength and height be able to reach his arm into this area to undo a bolt? Whatever the task might be, occupational biomechanics would be the field that one would look to in helping to design the systems and the tasks. I won't go through all of these in general, in specific, I should say, but here we're dealing with the various elements that go into occupational biomechanics and ergonomics, the various methods, if you will, to improve performance and reduce risk of medical trauma. So one would be able to refer to that from the charts, which I understand you'll all be getting a link to tomorrow, so you'll have these charts as well. So mental workload, I think I may have mentioned this previously. Tasks are becoming more and more cognitive over time, and mental workload is the portion of that operator's limited mental capacities that are required to perform a particular task. So you can think of it as a human has a resource that is their cognitive capabilities. And for any given task, that task may utilize a portion of those cognitive capabilities that gets a portion to that task. And so your reserves are what's left over. That's how much extra cognitive capability you have for attending to everything else. It's not being used for that specific task. So one uses your attention, if you will, to voluntarily match mental capabilities to the mental resources that are required for a given task. And why this is important is one wants to design tasks to utilize the proper amount, if you will, of mental workload. It's actually dangerous to have too much or too little, and I'll talk about that in a moment. If all of your attention and mental capabilities are performing one task, then you have no spare cognitive capability to attend to anything else that may come about. This last bullet here, increases in mental workload often precede performance failure. I used the example when changing lanes in a car and a passenger is in your car. If you're changing lanes on a busy freeway, you're devoting for that moment or two, because of the safety that act, all of your, or a large percentage of your mental workload to the act of changing lanes, and that passenger intuitively realizes that they're not just going to quickly and loudly launch into some new exciting story at that exact moment, because they do not want to overload your cognitive reserves, if you will. So human factors engineers come up with models. They come up with information processing models that describe how human sensory, cognitive, and motor capabilities work. And then they design experiments to test these models and to see how accurate they may be. And there's often elements such as short-term memory, long-term memory, attentional resources, sensation and perception. These are different models of information processing memory, or information processing in general, and they're useful in both designing and evaluating systems. I spoke about how you want to have the right amount of mental workload, and that is because if you have, and I spoke about the case of having too much, and how that can be dangerous, and one's unable to accomplish tasks safely and efficiently if you're overloaded. But there can also be a dangerous condition if you have too little, and it's under the topic of vigilance. And that is, if you're doing a task that requires very low amounts of cognitive resource for a very long period of time, your reaction time, your attention to what's happening in the environment will degrade. rather significantly, actually. Think of a long-haul flight, let's say from the United States to Asia, where you have pilots that are on the flight deck and needing to attend to the proper functioning of the aircraft for 8, 10, maybe 14 hours. And you want them to be responsive should something come up. You want them to notice if things come up too. So that would be an example of very low cognitive, or it's a vigilance issue basically, where you have an environment where there's very few events per unit time, and it's easy for the operator to zone out, if you will. Here's an image of probably a TSA officer looking at scans, and if they're doing that 6 to 8 hours at a time, it's very monotonous and long. It would be a task that would be easy to miss something, if you will. There's many examples of vigilance issues in the literature. So one of the areas that I get involved with quite a bit, is intellectual property cases related to user interface design issues. So human factors incorporates user interface design. That's a big part of it, designing interfaces to take into account how people work with technology. And there's various attributes that go into designing good interfaces. We want to design a great match between the user's needs, their skill level, their ability to learn, and if you can do that, you'll create satisfied and productive users. Excellent interfaces will be easy to learn. They'll capitalize on past experiences of the user so they can pick it up without excessive training or potentially without any additional training, depending on the complexity of the system. We want to encourage users to experiment and try out new features in a safe environment, if you will, where they're not going to crash the system or cause something unsafe to happen. And a good user interface design goes a very long way toward selling the system, not only to the users and their desire to procure and utilize such a system, but for the company itself, it's the user interface of software is really the visible part of that software. Users aren't even aware of what's going on behind the scenes. I like to call it's like the iceberg. The user interface might only represent 10% of the source code that was written to create that software. But so like an iceberg, you only see the top 10%. There's 90% that's underwater there. That represents your entire computer program. But when you see an iceberg, your perception is just that top 10%. And that's your perception of the whole iceberg. And that's what people's perception is of software. It's to them, to the vast majority of people, the software is the user interface, and it's about the goodness of it, and the features and functionality are evaluated for that software based upon the capabilities and limitation of that user interface. So when designing user interfaces, how should that be best done? Designers try to strive for consistency. That's really important. You don't want something inconsistent about that. Design, we want to enable shortcuts so that expert users can be more productive and reduce keystrokes, offer informative feedback, simple error handling, encouraging experimentation, easy reversal of actions. That's basically undo capability, internal locus of control. We want the users to feel that they're making things happen in the software versus just being responsive to what the system is doing, reducing short-term memory load. So let's go on to attributes for increasing safety. Oftentimes, human factors engineers and the attorneys that work with them are involved with cases that have to do with safety. Not always. In the intellectual property arena, it's often about, inventions and similarities of one invention to another, but the example of trip and fall is also very common, or other accident cases in which safety is a critical component of the case. So here are some attributes that are important for increasing safety. I'm going to speed up a little bit because I don't want to run out of time. Interesting that, okay. So I brought this chart because I wanted to make a point here. A lot of the research is saying that sometimes you read 70% plus, sometimes you read 80%, that accidents in the aviation field are from human causes. This shows a graph over time. It's a little bit notional, but in the early 1900s, most of the accidents were caused by technical causes, and now in the present time, most of the accidents are caused by human causes. So what they're really saying here is that the accidents were caused by the operators at the time of the accident. Because when you really think about it, all of my contention, and it's, I think it's echoed well in the field, is that all accidents are human causes. It just depends on the timeline. If there's a technical accident, if this actuator on this flat failed or this hydraulic pump failed, when you think about it, that hydraulic pump didn't just come into existence magically. It was designed by a team of aeronautical engineers, and they made design decisions about how it was, the shapes and the materials and the processes. So if it failed, there was most likely some degree of human culpability, if you will. Human decision-making led to that failure. So I just wanted to make the point that sometimes I hear it say, oh, well, that was a technical failure. That was a human failure. Well, really, to me, it's all, not all, but a large percentage of accidents. And you can think of this beyond aviation, too. There really is some human culpability somewhere that just depends on what stage. Okay. I think many people are aware that accidents, especially in complex systems that have been designed to be very safe, they're usually caused by a cascade of errors, multiple smaller errors that perhaps in isolation wouldn't have been an issue at all. But if they line up just right, it can cause a much more catastrophic error. Here's a listing of various kinds of accidents that happen in the United States as far as motor vehicle-related deaths, deaths due to falls, poisonings, cost of workplace deaths estimated at $48 billion per year, with an average cost of $780,000 per victim. And if you divide that by all of the workers, it's $420 per worker. So anything that can be done to reduce those numbers of accidents, injuries, deaths, is definitely good for society. Here's the most frequent cause of workplace deaths and injuries. I won't read all of these. You'll have this in the presentation should you choose to download it after. Most common ones. So let's talk a little bit about safety legislation. So prior to the 1900s, as you may well imagine, employers assumed very little responsibility for safety. The companies defended themselves against liability for accidents, claiming contributory negligence, negligence due to the actions of fellow employees, and the injured worker was aware of the hazards and knowingly took the job and assumed the risks of that job. So worker compensation came along for workers for on-the-job injuries, regardless of who was at fault, and they were thrown out actually in 1917. But today there are different forms of worker compensation laws that vary by state, and approximately 80% of all workers are covered. There's typically three criteria here that the compensation needs to. The injury must have these attributes, obviously arise from an accident that was at the place of employment of that employee, that was part of that employee's job responsibilities. So all of those need to be true. And what were the goals of the goals for establishing workers' compensation? Well, it was to provide income and medical benefits for the victims and their dependents. It was to provide a single remedy to reduce court actions, costs, and workloads arising out of perennial injury litigation, to eliminate payments of fees to lawyers and witnesses, as well as time-consuming trials and appeals. Obviously, that still goes on, but I think worker compensation has reduced it. We're encouraging employer interest in safety and rehabilitation. Encouraging employer interest in safety, I think that's probably one of the best things that have come out of worker compensation legislation, and promote the study of causes of accidents. Two specific bodies are worth mentioning here. OSHA, Occupational Safe and Health Administration, formed in the 1970s. They're set up by the federal government to impose safety standards under the Department of Labor. They cover various different industries, primarily record keeping and understanding the statistics and a lot of different information on a lot of different occupational, a lot of different job types, if you will, and safety information about it. And then there's NIOSH, National Institute for Occupational Safety and Health, and they are a research and educational organization, I should say, and they find various hazardous types of working conditions by reviewing research and set standards in which companies can comply to and should comply to, and oftentimes are regulated and forced to comply to. So there's a lot of product liability suits that would incorporate human factors because obviously it's design of the product. Suits filed against the company claiming a product was defective and therefore caused an injury or death. An example is the McDonald's hot coffee case. I think the second bullet is illustrative here, which is the product defective or inherently dangerous? A car seat and a sharp knife. Well, they're both products, sold by potentially two different companies for two different uses. And in normal operation, they both can be very useful products, but some products can be inherently dangerous. Thinking of hot coffee, I mean, that's potentially a dangerous item too. So there can be a lot of ways to argue, if you will, from a legal point of view, the issues around products and defective products, inherently dangerous products, proper use, basically, and that gets into my last point here. Is the product defective, or was it failed, i.e. it failed to perform safely as it would ordinarily be used, or did the person or persons utilize it in an unintended manner? Was the way it was used foreseeable? Should that manufacturer have done something to either warn the person or persons not to use it in that way, or to make some sort of safeguard so it couldn't be used in that way? These are all issues that could be considered. So factors that contribute to accidents, primarily human factors engineers take a systems approach and they look at the whole environment where the accident took place. There was the question about trip and fall. Some of these slides may start to answer some of those questions. They look at the person that was performing the task. I mean, maybe the task was just to walk from A to B. What that task supposedly was. The task itself, the person that got injured and the attributes of that person, any equipment that was directly or indirectly involved, and other factors such as the social or psychological environment. So looking more closely at the job characteristics and equipment, was there a high physical workload required or high mental workload? Monotony, that has to do with the vigilance issue I was talking about earlier. Equipment, that's where a lot of the safety analysis is performed. So the equipment itself, going back to the trip and fall, a simple trip and fall is maybe the equipment is nothing more than the types of shoes that they were wearing, or was there a hose or a rake or something that made for an unsafe environment. But in a more complex case, you're looking at controls and displays, computer software. Some of the environmental issues may include electrical or mechanical hazards, different toxic materials, the physical environment, what was the illumination like at the time, noise and vibration, temperature, humidity, various kinds of hazards. So it's important to take a systems approach in analyzing accidents to figure out where blame may lie, if it does, in either prosecuting or defending against claims like that. Some of the personal characteristics that should be looked at, such as age and gender. There was a question about accidents and children. Here's one statistic I found, although I don't have the reference here and would require more research, that 15 to 24-year-old males experience more accidents than other age groups. That seems like common sense to me. I would be able to find some very, relevant literature that would point to various accident probabilities in age groups and how different characteristics of different age people may contribute to or protect against accidents. Job experience, I felt this was interesting in that 70% of accidents occur within the first 3 years for any specific job. And that's because the people are really learning how to do their job efficiently and safely. Stress, fatigue, drugs, and alcohol obviously impair operator performance and lead toward accidents. And lastly, and this is really important too, the social environment. What are the social norms, the management practices, morale, training incentives associated with the environment in which the accident took place? Here's a quick example. if you don't wear safety glasses, if none of your colleagues are wearing safety glasses on the job, you're probably not going to be the only one on the team that's wearing safety glasses, or I don't want to say probably, but it may lead to a more likely chance that you would choose not to wear safety glasses so as not to stand out in your social environment with your coworkers, even if management and their employee handbook says thou shalt wear safety glasses. Human error is usually triggered. So this goes back to my earlier point about all errors can potentially be human error. This is kind of saying the same thing in an opposite way. Pilot error is blamed on 70+% of airline accidents, but really it's, I don't know if I have enough time to really go into some of the more issues of this bullet. But basically, I think maybe a quick takeaway here is just the number of errors and where blame is attributed to. I guess I just wanted the audience to think about that. One of the things that I thought was interesting in intensive care units, there's an average of 1.7 patients per day that experience errors. Some of them very life-threatening, life-critical errors that are performed by the healthcare professionals that affect the attendees at the ICU. The Gordon and Betty Moore Foundation, Gordon Moore, one of the founders of Intel, set up a foundation to look at errors in intensive care units after Betty Moore had a bad experience in one, and they're donating millions of dollars just looking at this one issue. There's various kinds of errors, so errors of omission, errors of commission, failing to perform a procedural step that was important, that's an error of omission. An error of commission is performing an extra step or performing a step incorrectly. And this is, I have 3 charts, I think, coming up. I probably will go very quickly given the time. But I have 3 quick charts on showing where errors can happen. You have stimulus coming in. You have a situation assessment, which is your knowledge, mapping that stimulus to your knowledge. There's the application of a rule. This is your plan or intended action. This is executing the action. This is using your memory, what happened previously. So errors can come in at all stages of this, stimulus to execution cycle. And in the interest of time, I'm not going to go through, I think, these 3 slides that talk about mistakes and the 2 kinds of mistakes that can happen, the various kinds of slips that can happen. That's where you have the right intention, but it's incorrectly executed. These, by the way, are places in which a human factors engineer can assist attorneys in understanding why an accident took place and explain it in a clear way to the court or the jury so that there's an understanding of how the system could or should have been better designed or why the system was designed in a proper way. Errors.
Craig, this is Carl. Let me just interrupt you for a second. If you, during the presentation, if you feel that you need to go over our time, I'm sure that's fine if we go over just a little bit because I wouldn't want you to miss out on important information that you feel is relevant for the audience. So I just wanted to point that out to you. And we only have a few questions left, so, please feel free to cover any important information that you feel is necessary.
All right. Yeah, I think I only have about 5 more slides or so I should be wrapping up very soon anyway.
Okay, that's fine. Great.
I thought this was a very interesting slide, too. So let's say there's a component that you have in your system that has a 90% chance of operating correctly. And so if any given time, I'm just using a very easy number there, 90%. You go to use your system, you have a 90% chance of it working correctly and a 10% chance of failure. So let's say now you arrange these two components in series so that it's important that both of the components operate successfully in order for your system as a whole to operate. Well, in that case, the probability that your system as a whole operates is only 81% chance, and your probability of failure is a full 19%. So you've really increased the probability of failure tremendously by putting those two components in series. In other words, they both need to work simultaneously for your system as a whole to work. Alternatively, if you put these two components in parallel, where either or of these two components need to work and for your system to work, so think of a redundancy or a failover, some sort of system in which you have the primary unit, but if it fails, it goes to the secondary unit. Then, and this is used all the time in engineering, it's because of this simple math here. The probability of it working now goes up to 99%. When you put your two 90% probability of success components in parallel, now the probability that either one is working, at least one is working, is 99%, and the probability of failure is only 1%. So I thought that was interesting to show. So how do we reduce errors? How do we prevent errors? Through the proper design of the task, taking into account working memory, there's other things in designing the equipment itself, going to minimize confusion, perceptual confusion. This is talking about shape coding, actually. In the cockpit, the flaps control, it looks like, is shaped like flaps, where it's thicker on the front and narrow on the end, so you can feel what that feels like without taking your eyes off the other instruments or out the windscreen. The landing gear up and down in an airplane actually feels like the wheel of a plane. It's shaped like a plane. So that's ease of discrimination. Make consequences of actions visible. I spoke about that earlier. Lockouts of making the system bomb-proof, as I said earlier, not allowing the wrong action to take place. An example, a car won't allow you to lock it unless the keys are in your pocket or outside of the vehicle, I should say. Various kinds of reminders can be incorporated. Okay, so proper training, especially in more complex simulations. Simulation can be used in more complex systems to allow operators to train in very rare normal events. We want our pilots to be able to practice how they would respond if there's a bird strike, let's say, and some of their engines go out, or if there's a failure in an actuator and they don't have use of their rudder, or various kinds of critical operations. We'd love them to be able to practice that in an environment that is safe for them to practice. So simulation can be used quite a bit. Various kinds of checklists that this first got its start in aerospace, but now it's really spreading to medicine and many other fields where there's rules and checklists that the operators apply to make sure that they haven't missed anything, everything's set properly, designing error-tolerant systems. Accident investigation. So again, going back to the trip and fall question, I think this applies to something, as relatively minor as, a single individual falling to the ground all the way through a major chemical spill, let's say, or a nuclear power plant accident. The various components of accident investigation still apply across that spectrum. We want to interview witnesses as soon as possible, inspect the accident site before changes occur, take photos, videos, record pertinent data on maps, get copies of all reports, obtain documents concerning the normal operation, normal procedures, maintenance that was performed, any reported abnormalities. We want to take accurate notes for the entire investigation so it's well documented. Anything that can be done to record the pre-accident condition, the sequence, reconstructing the accident using simulation and visualization is often a very effective technique to explain to others what likely happened, document location of the victim's witnesses, machinery, etc. And implementing safety programs going forward, if we're talking about companies wanting to reduce their liability and their risk, identify what those risks are, implementing various safety programs, including management involvement, accident investigation, rules, personnel, personal safety equipment, protective equipment, training, promoting safety, perhaps even incentivizing safe behavior through various incentive mechanisms, and evaluating and measuring the program effectiveness. So my last slide has to do with risk-taking and warnings. Risk-taking can be thought of as a decision-making process in which they should know that what the hazards are, that the hazards exist, what their range of actions might be available at any given time, and what the consequences are of safe behaviors versus of the alternative behaviors that they might take. And having written or graphical warning labels are important and can help in that assessment of risk-taking decision-making process. So to finish up, my name is Craig Rosenberg, and I do a lot of expert witness consulting. I run an engineering design company called Global Technica and work in these various areas. I enjoy talking about human factors and have enjoyed the opportunity to present to you today.
Okay, Craig, thank you so very much. And we do have a couple of questions before we end our program today. And here's a question from Rachel. She states she has a case where a gal was crossing a busy street and was struck by a car. She crossed from west to east, covering 3 lanes of traffic. Just before she reached the median or the middle lane, a car coming from the northbound traffic entered the median turn lane. Our gal saw this car and froze in lane 3 of southbound traffic and was nailed by a car in lane 3. We have been discussing getting a human factors expert. Do you have any commentary on using human factors experts in pedestrian crossing accidents?
Yeah, my comment to the person asking the question, it really has to do largely with that last, the second to last slide. I talked about accident investigation, where you're looking at the full environment which the accident took place, trying to document as well as possible what the conditions were at the time of the accident. And I think using simulation, using a computer graphics visualization can often be very instructive, both for explaining what likely happened to the various parties involved, and as well as a human factors report, from an expert human factors engineer showing giving, their expert opinion as to the various contributory factors as to what led up to that accident. And as I mentioned in my presentation, there can be a lot of different aspects to consider, and in taking that systems approach, the interaction between all of the various elements can help the expert form their opinion as to, where culpability may lie, if you will, or for that. So I guess those are some of my thoughts there. I think visualization can be very helpful. It's often used in accident reconstruction. Many of you have probably seen computer graphics animations that show what may have or what likely happened combined with an expert report. I think that all those can be helpful to attorneys in laying out their positions.
Okay, and then just one final question. There's an attorney who writes, I have a case involving changes to a traffic pattern. How long should a warning be given to drivers before they would become familiar with this change?
I guess I would need a little more detail as to, it's not quite clear in me what the environment is that's being discussed, and it's something I could, if contacted after, my contact information's on the screen, so I guess I would encourage that attorney to contact me afterward, and I'd be happy to lend an opinion. Oftentimes the answer, though, there isn't 5 seconds or 12 seconds or some number. It would be rare that any professional engineer can just jump up and say a specific hard constant number, that covers a wide variety or all of the possible conditions. And because, the real answer and the most honest and accurate answer is it depends. And it depends on all of these various factors that I've been mentioning in my presentation. And in looking at several or many of the factors in combination, one can come up with a good justification of what that number should be. But to say, a warning, how long should a warning light be displayed or something like that? Well, it depends on what's the user population, what's the task at hand, how safety critical is this? If something goes wrong, are we talking about a toaster and you're toasting your toaster? Are we talking about an indicator that the reactor's melting down? There's a wide range of engineering applications to warnings, and the most honest and accurate answer is it depends, really. So I'd be happy to lend my opinion on that after.
Okay. I think that's the end of our questions for today. And just for again, CLE information, this webinar is eligible for CLE in California, Illinois, Minnesota, New Jersey, and Pennsylvania. We have asked everyone to enter their code word for today. And again, one other item is the TASA Group does offer additional services and reports for any of your testifying needs that you may have for experts, whether it be e-discovery or document management, free interactive webinars, which we've all participated in today. And I would ask that if anyone has any suggestions of topics or subject matters, please let us know here at TASA. We have the ability to reach out to many experts in many fields, as you know, and we are happy to help develop webinars that are of great interest. We also offer research reports on expert witnesses, and those are also available for you. And if you have a need for any of those reports, again, please give us a call here at TASA. I want to take this opportunity to thank everyone for attending, and most especially Dr. Craig Rosenberg for his time and effort in creating this presentation. If you would like to speak with Dr. Rosenberg, or if you would like to speak with a TASA representative regarding any expert needs that you may have, please give us a call. Our number is 1-800-523-2319. Or you can reach us by email, and you can reach me, Carol Kowaleski, at tasanet.com. And again, a link to this webinar will be sent out to everyone tomorrow, so please look for that in your email. And if for some reason you don't get it, please feel free to give us a call here. Thank you again, and that is the conclusion of our presentation today. And Craig, thank you very much for your time.
Thank you for having me. Appreciate it.
Bye-bye all.